For our second lesson in Unit 6, we're going to dig deep into kites and trapezoids. These are figures that you've explored in your elementary and middle grades a little bit, but we're going to have obviously the high school spin on these things, building on prior knowledge. If there's not prior knowledge there, that's okay. These are called kites and trapezoids, so we're going to explore these. These are quadrilaterals, and so we know that we're going to have constraints to the fact that there are 4 sides in these figures, and there are 4 angles in these figures, and the sum of those 4 angles is 360 degrees. They are polygons, so the sum of their exterior angles is also 360 degrees. And so here is what a kite is. A kite is a quadrilateral that has 2 pairs of adjacent congruent sides, but the opposite sides are not congruent to each other. So these are congruent and those are congruent. These are not, these are not. These can't be congruent, these can't be congruent. So a kite, again, has 2 pairs of adjacent congruent sides, but no opposite sides congruent. We've drawn in these diagonals here just to sort of let you know a little bit about the kite. You can probably tell that those diagonals look perpendicular, and that is the case. A kite has 2 pairs of opposite sides that are not congruent, 2 pairs of sides that are congruent, and what I want for you to recognize is that this is equidistant from those points, and D is equidistant from those points. And so what we can show here is that we have a pair of congruent triangles, the big triangles, DAB, DCB. These triangles are congruent to each other using some side-side reflexive side, which means that these angles here are congruent, these angles here are congruent, and then the big angle at A is congruent to the big angle at C. We do have to think in terms of congruent triangles in this unit. We're not going to do too much geometric proof, but we do have to do our geometric thinking, relying on our expertise and our experience from last unit. So this is kind of an interesting concept here. We know that these points, B and D, lie on the perpendicular bisector. So I make this statement, this is a little awkward of a statement to make, that these are equidistant from those endpoints of this segment AC. Because what that tells us is that this segment is perpendicular to segment AC. Now we can prove that otherwise, as we already did back in our 4-6 assignment. The last item we had triangle like QE, maybe E was here, like Q, I don't know, whatever it was. It's like QUE and QEA or whatever else like that. It was just kind of a weird situation, but we proved that these 2 triangles, these medium-sized triangles, were congruent to each other. And that was after proving the big triangles were congruent. So hopefully you remember that from 4-6. If not, I'll show you the picture in class. Maybe it should be included in the video, but alas, here we are. So we know that these 2 triangles are congruent, which means that these 2 angles at X are congruent to each other. And if they're congruent and supplementary, then that means that they are right angles. So this was a theorem that we would have proved in Unit 5, but we didn't prove that in Unit 5. And so here I'm just explaining why these are right angles. So, since those angles are right angles at X, that means that we can do some fun thinking here. And so I'm going to do this. I would like for you to do this. Now I would like for you to do letter B. So pause it and draw the pictures if needed. But here we're going to find the measure of angle 1, which is here, and the measure of angle 2, which is there. We know that this is 22 degrees. And we know that this big triangle here is congruent to this big triangle there, again, by side-side reflexive side. Right, pair sides, reflexive side. So I know that this angle is also 22 degrees. This is 22 degrees, that's 22 degrees. And so we can do a little bit of thinking through this to recognize, first of all, that, hey, these diagonals are perpendicular. All right, so those are perpendicular, which means that all 4 of those angles are right angles. If lines or segments are perpendicular, it means they intersect to form right angles. And so those are all right angles. So we know the measure of angle 1 without doing any work. We've said earlier that this segment is the perpendicular bisector, right? So these are congruent and it makes right angles, all right? So that gives us now a right triangle where I can say, hey, if I just focus on this right triangle here, I know that the sum of the measures of these angles is 180. Or I can focus on the fact that this triangle is isosceles, these angles are congruent, these are each 22, so 22 plus x plus x has to add up to 180 if I wanted to focus on this big triangle. A couple ways you could approach this. I'm going to focus on the fact that this is a right triangle, so these angles need to add up to 90, and they do, and so that means that the measure of angle 2 is 68 degrees. All right? Hopefully that makes sense for you. If not, please make a note in your notes to ask a question. If you don't ask a question, then I don't know that you didn't get it. Over here, I want you to try to do this one. Find the measure for angle 1 first. Use it to find the measure of angle 2, measure of angle 3 as well. So find those measures on letter B. All right, and now let's talk about trapezoids. Trapezoids, again, you're familiar with this idea of trapezoids. Trapezoids have a pair of parallel sides, but the other pair of sides cannot be parallel, otherwise it would be a parallelogram. So a trapezoid is a quadrilateral that has exactly one pair of parallel sides. It has a pair of parallel sides and another pair. It's exactly one pair of parallel sides. The other pair cannot be parallel. Just because they're parallel doesn't mean they're congruent. In fact, if they're parallel and congruent, it can't be a trapezoid, it would be a parallelogram. We'll prove that later. So here, these parallel sides are not congruent. Now the other non-parallel sides may be congruent. If the non-parallel sides are congruent, this is what we call an isosceles trapezoid. It looks like a isosceles triangle that got the head chopped off, all right? And that actually is what an isosceles trapezoid is, all right? So the non-parallel sides in an isosceles trapezoid are congruent. That should not be new vocabulary for you, but then again, I don't know what has happened with you over the last several years, and so if you did not know that, now you do. And the expectation is that we're able to identify the difference between a trapezoid and an isosceles trapezoid. The nuance there, right? They're both trapezoids. They have all the same characteristics as trapezoids, but isosceles trapezoids are extra special. For example, theorem 6.4, the base angles in an isosceles trapezoid are congruent. If this is an isosceles trapezoid, think if this were an isosceles triangle, we would know that these angles are congruent to each other. Well, that's going to be true in this particular situation. We can prove that with a couple of approaches, and we'll kind of explore that a little bit later. But these angles right here, these are same side interior angles, parallel lines, transversal. So these have to add up to 180, and these have to add up to 180, which means that these have to be the same. These are congruent supplements, right, of congruent angles, so they have to be congruent to each other. Furthermore, the diagonals in an isosceles trapezoid are congruent. The proof on this is not too bad. If we look at this as a pair of overlapping triangles, this triangle and then that triangle, we have side, base angles congruent, reflexive sides. So these triangles are congruent. It means that these diagonals are congruent as well. All right? And so the the diagonals in an isosceles trapezoid are congruent. The base angles in an isosceles trapezoid are congruent. And so we can use that to do some thinking, some practice, some work. And it might require a little bit of thinking for us. So pause the video, draw the pictures as needed. And here we're going to show that these base angles are congruent. The measure of angle 1 is going to equal the measure of angle 2. The measure of angle 3 is going to equal 111. Oh, that's done. So I've solved for the measure of angle 3. That's great. These have to add up to 180. And then these are going to be the same. So these add up to 180, these add up to 180, these are the same. You don't have to solve twice for the measure of angle 1 and angle 2. If you solve for the measure of angle 1, then that gives you the measure of angle 2 without having to do work. All right? And so that's what I want for you to see. Can you create this equation that these are supplementary angles? They are same side interior angles. You've got parallel lines, and you've got a transversal. So this obtuse angle and this acute angle, these are same side interior angles. All right, hopefully you can recognize that and you can create your equations based on work that we did in chapter 2 last semester. Over here, solve for x. It marks these segments, TV, US. This is an isosceles trapezoid. And so we know that the diagonals are congruent. So our equation is that 2x minus 1, I'm trying to find space here, 2x minus 1 is equal to x plus 2. And solving that equation is not too terribly difficult. Go ahead and you solve it. These are equal to each other. You solve. Do that basic algebra 1, chapter 2, and then we'll confirm your answer in class. Pause the video if needed. And now we're going to discuss the mid-segment. And this should probably be the end. I think that this is the last, this is the last thing. All right, so the mid-segment of a trapezoid is a segment that connects the midpoints of the non-parallel sides. All right, that is a mid-segment in a trapezoid. All right, it doesn't have to be an isosceles trapezoid, but a mid-segment in a trapezoid connects the midpoints of the non-parallel sides. All right, so here x is the midpoint of this non-parallel side, y is the midpoint of that non-parallel. So these are the non-parallel sides, x is the midpoint, y is the midpoint, and this segment xy connects those. So if we have a parallelogram, trapezoid, what we're going to find out is that the measure of this segment is actually the average of the lengths of the parallel sides. All right, so kind of an interesting fun fact. XY is parallel to both of them, all right, and it is the average of the length, 1/2 times the sum of their lengths. That is theorem 6.6. The midsegment of a trapezoid is parallel to the parallel sides of the trapezoid, and it is the average of the lengths of those parallel sides. So this right here, this formula, this relationship, might end up being a little bit tricky for folks, and that's okay if it is. I know that there's a fraction involved here. And so if you want to, you can understand that if I multiply both sides by 2, I would get this relationship. If this is a little bit easier for you to understand, I would like for you to write it down as well. Actually, regardless of if it's easier, I want for you to write it down as well. But if I multiply both sides by 2, and now I don't have to deal with a fraction. All right, many of us, we freak out when we see an equation that involves a fraction, all right? And you know, maybe with good reason. This is America, right? We struggle with fractions. And so let's do our best to maybe think about avoiding those fractions. How can we set ourselves up for success? And so this is one way in which we can do that. Given these trapezoids, find the lengths of the given segment. Here it's find the midsegment. Here is find the other parallel side's length. So these are trapezoids, which means that the length of xy, this midsegment, is equal to half the length of KL plus JM. All right, so this is kind of a weird equation because we have a number, but then we have an expression, and then we have another expression. All right, so this is a little bit messy, and let's try to figure out how we can think through this. You may find it valuable to double both sides. All right, I'm going to substitute in my numbers. We don't know the length of KL, that's what we're looking for. JM is 4/5 times XY. All right? So this is our equation based on the theorem from the last slide. The length of the midsegment is half the length of the sum of those lengths. All right? Or half the sum of those lengths. So here, I know that XY is 2/5, is 25. So I'm going to substitute that number in, and we're going to do a little bit of work around that. 4/5 times 25. All right, so this equation, this setup here is a little bit threatening for folks because we see fractions, we see parentheses, we have to multiply, we have got to do some work. But folks, ask yourself, do I get it? Does this make sense? And ask yourself that question. Does this make sense? Does this make sense? If you are thinking while you're writing this, then you can assess yourself as you go to say, this step made sense, this step didn't. Or I got lost in that. So if you're getting lost in it, then where did you get lost? Did you get lost in writing the equation? If that's the case, let's go back and look at what the equation is supposed to be. All right? Did you get lost when all of a sudden there's numbers involved? Okay, well, here's where the numbers are. Here's where we get 25, right? That's XY. 4/5 XY. XY we know is 25, so we're going to put that number in there. Let's kind of think through this as is. And then we'll try to figure out the best way to handle this fraction in this. Do we distribute or do we do something else? All right, 4/5 of 25. You can use elementary math to multiply that, or you can use a calculator. And that gives us this situation. Now, many of us want to distribute that 1/2, and you can do that. You are allowed to. My recommendation is multiply both sides by 2. If you multiply both sides by 2, now you do not have a fraction, and you do not have to worry about the parentheses grouping that sum. All right, and it makes the work pretty easy to do your solving. All right, that's my approach. That's my recommendation. Now, many of you are programmed from Algebra 1 to say, we've got this fraction, so I have to distribute the 1/2 to get 1/2 of KL and 1/2 of 20. That's fine. You're welcome to do that. Subtract 10 from both sides, and then multiply both sides by 2. You're going to get the same answer. You just did an extra step of work. Again, I'm fine with you doing extra work. Usually you don't want to do extra work, and so my exhortation would be, think about the relationship here, double both sides, and then you don't have to do that extra step of work. Again, it's just a suggestion. All right, find the length of PQ here. This one, I want for you to do. All right, here, we were given the length of the midsegment, and we had to think backwards. Here, we don't have the midsegment. Your job is to find the length. This one you should just be able to plug and chug. There's not really any solving to do in that one. Do that one. If you get stuck on it, all right, then I expect you to ask a question about it in class. Don't just write IDK. You need to do it if you want to get full credit on this task. Hopefully you understand relationships and properties of kites and trapezoids. All right, we're using triangle congruence to explain that thinking and to understand the relationships within the angles and segments and diagonals in those figures.